Hello everyone. In this video, we will talk about the Poisson process. Before getting into the Poisson process, we will talk about counting process. A counting process n of t, where t greater than or equals to 0, represents the total number of events that have occurred up to time t. For example, nt equals to the number of customers that have entered into the supermarket by time t, or nt equals to the number of goals a particular hockey player scored by time t. Nt is a random variable. And since nt represents the total number of events that have occurred, nt must be greater than or equals to 0, and nt must be an integer. And ns is less than or equals to nt for s less than t. Between time 0 and time s, the total number of events that have occurred is denoted by ns. And for t greater than s, in the time interval from time 0 to time t, the total number of events that have occurred is represented by nt. So ns must be less than or equals to nt. The number of events that occurred in the interval st is denoted by nt minus ns. A counting process is said to possess independent increments if the number of events occurring in a given interval is independent of the number of occurrences in any other non-overlapping intervals. For example, we have an interval t0, t1, and another non-overlapping interval t2 and t3. The number of events occurring in the time interval t0, t1, and in the time interval t2, t3 are independent. A counting process is said to possess stationary increments if the distribution of the number of events occurring in any time interval depends only on the length of the time interval. For example, we have an interval from time t0 to time t0 plus s, and another interval from time t1 to time t1 plus s. Both the two intervals has a time duration of s unit of time. And in this case, the number of events in the interval t0 to t0 plus s and in the interval t1 plus s has the same distribution. Let's get into the Poisson process. Some applications of Poisson process, which is to model the occurrence of events over time. For example, to model the number of vehicle accidents at a traffic intersection, the number of earthquakes or floods in the region, data packets arrive at a certain node across network connection, particle emissions from a radioactive source, emergency calls received at a hospital, car arrivals at the drive-through window of a fast food restaurant. Then, what is a Poisson process? The counting process nt is said to be a Poisson process with rate lambda greater than 0 if the following conditions are satisfied. n0 equals 0. At the very beginning of the time interval, there's no event occur. The process has independent increments. And the third condition, the number of events in any interval of length t follows a Poisson distribution with mean lambda t. That is, for all st greater than or equals 0, the probability that n of s plus t minus n of s equals small n The random variable n of s plus t minus n of s corresponds to the total number of events occur between time s and time s plus t. So this corresponds to an interval with length t. And this probability follows a Poisson distribution with mean lambda t. And this is the corresponding PMF. The parameter here is lambda t, where n takes on values 0, 1, 2, up to infinity. And this third condition corresponds to saying that the process has stationary increments. Let's take a look at an example regarding this third condition. Suppose you have a random variable, say n5. Okay, so what is this? Okay, according to the PMF, here we have t equals 5. So if this is a Poisson process random variable, n5 follows a Poisson distribution with mean lambda times 5 or 5 lambda. So we have the following PMF. The random variable is n of 5. And this number 5 corresponds to an interval with length 5. So we can have a time interval between 0 and time 5. This is n5. And this can be also expressed as n5 minus n0. We can consider any other interval with length 5. For example, from time 12 to time 17. The number of events occur can be modeled by the random variable n5 as well. We can write this as n17 minus n12. How about the property of independent increments? We have two non-overlapping intervals. Suppose I want to find the probability that there are exactly 2 events occur between time 0 and time 5. And the probability that there are exactly 2 arrivals between time 12 and time 17. I want to find the intersection of these 2 events. We have non-overlapping intervals, and the Poisson process possesses independent increments. So this probability, exactly 2 arrivals between time 0 and time 5, and exactly 2 arrivals between time 12 and time 17, can be computed as this. The probability that n5 equals 2 corresponds to the first time interval times the probability, again, the same random variable, n5 equals 2, corresponds to the second time interval. So this is the independent increments of a Poisson process. Let's wrap up the random variable nt. The distribution of the number of events nt. Nt is the number of events occurring over an interval of length t, follows a Poisson distribution with mean lambda t. So you can see the similarities, where n takes on values 0 up to infinity. The mean is lambda t, and the variance is lambda t. Here, lambda is the constant rate of occurrence of events in the process. And recall that the distribution of the number of events occurring depends only on the length of the period t. Let's take a look at an example. A radioactive source emits decayed particles at an average rate of 4 particles per second according to a Poisson process. In a 1-second interval, find the probability that exactly 3 particles are emitted. Let n1 be the number of particles emitted in a 1-second interval. The number 1 here corresponds to the time interval 1 second. Here, the average rate is 4, so lambda equals 4, and t is 1. So lambda t equals 4 times 1, which is 4. Nt follows a Poisson distribution. Because this is a Poisson process, we have n1. The random variable is n1. So n1 follows a Poisson distribution with parameter 4. And we want to get the probability that n1 equals 3. Exactly 3 particles are emitted. Plug into the PMF. E to the power minus lambda, lambda is 4, and then times lambda raised to the power n is 3, over n factorial, over 3 factorial here. So we get the probability 0.1954. Consider the same scenario, but now we are interested in a 2-second interval. Find the probability that at most 1 particle is emitted. We have another random variable, n2. The duration is 2 seconds, so we have n2. n2, the number of particles emitted in a 2-second interval. We have the same value for lambda. Lambda equals 4. And then now t is 2. So lambda t is 8. n2 follows a Poisson distribution with parameter 8. We want to get the probability that n2 is less than or equals 1. This is P0 plus P1. Substitute into the PMF for x equals 0 and x equals 1, or in this case, n2 equals 0, n2 equals 1. Upon calculation, we get the answer 0.003. The next scenario. In a 3-second interval, what is the mean number of emitted particles and what is the associated standard deviation? And now we are working on N3, 3-second interval. The same lambda equals 4, and t is 3 seconds. Lambda t is 12. That is, N3 follows a Poisson distribution with parameter 12. Get the mean and the standard deviation of this distribution. The mean is 12, and the variance is also 12. So the standard deviation is the square root of 12, which is 3.4641. Let's take a look at the next example. Suppose a customer service center receives an average of 3 complaints per hour according to a Poisson process. In a 2-hour period, what is the probability that the customer service center receives 5 complaints in the first 90 minutes period and 2 complaints in the last 30-minute period? Here we have 2 non-overlapping intervals, the first 90 minutes and the last 30 minutes. Identify the distribution for the 2 intervals. The first 90 minutes, the lambda is 3, an average of 3 complaints per hour. And what is t? 90 minutes. And the rate is expressed as complaints per hour. So t equals 3/2. 90 minutes, 1.5 hours, 3/2 hours. And therefore, the corresponding random variable is n of 3/2. Follows a Poisson distribution with parameter lambda times t, which is 4.5. And then the last 30 minutes, lambda is still 3. And the time is 30 minutes. In number of hours, t is 1/2. The random variable is n of 1/2, follows a Poisson distribution with parameter 1.5. We want to find the probability that in the first 90 minutes, there are 5 complaints, and in the last 30 minutes, there are 2 complaints. This is a Poisson process, possesses independent increments. So this probability equals the probability that there are 5 complaints in the first 90 minutes times the probability of having exactly 2 complaints in the last 30 minutes. Plug into the PMF. The first term corresponds to a Poisson distribution with parameter 4.5 and n equals 5. The second term corresponds to a Poisson distribution with parameter 1.5 with n equals 2. Upon calculation, we get the answer 0.0429. That's it for today's video. Thank you for watching. In the next video, we will talk about continuous probability distribution.